Okay. Good afternoon, everyone. My name is Kristi Dulaj, and today I'd like to talk about a journey that begins over a century ago in a time of unprecedented discovery, in the year that we now call the miracle year of 1905. Among the miracles of that year, noise was born, and its birth, much like the concept itself, was anything but quiet. I'd like to firstly introduce you about the way it was born, significance it had, and misconceptions it aroused. Why was this year a miracle one that caused the scientific revolution of 1905 and Brownian movement? Lavoisier, Dalton, Gay-Lussac, and Avogadro's contribution in the field of chemistry. What was the atom debate and science, skepticism, and politics that were mixed in it? Scientific contribution of Oswald, Mach, Einstein, and Langevin, from equilibria to stochastic equations. Who was Charles Batchelor, the pioneer of financial engineering and stochastic processes, the impact of the vacuum tube and unraveling how this revolutionary device transformed not only how we perceive and harness noise, but also reshaped the broader landscape of electrical engineering. Later on, we're going to proceed into stochastic processes and we'll shed light on their applications and also explore the mathematics of noise. Noise entered the scientific stage in 1905 as a decisive force, resolving one of the greatest debates of its time, the existence of atoms. This contentious debate saw some of the most prominent scientists of the time deeply divided. Albert Einstein, with his knack of tackling big problems, devised a tool to establish the reality of atoms, and this breakthrough sparked an avalanche of profound ideas. Perrin validated Einstein's predictions and even utilized it to calculate Avogadro's number, leading to a Nobel Prize. Since then, noise has permeated various scientific fields, leading to numerous important contributions. Langevin initiated the field of stochastic differential equations within 3 years of Einstein's work. Albert Einstein revolutionized our understanding of the universe in 1905 with 3 miracles of that year. The first one was his theory of Brownian motion, which he provided evidence for the existence of atoms. The second was the explanation of the photoelectric effect. And the third was the special theory of relativity. Einstein published 5 papers on the subject, including theoretical observations of the Brownian motion and the elementary theory of the Brownian motion, which connected Brownian motion to diffusion. These 3 miracles revolutionized our understanding of matter and light and our perspective of reality. He later continued to publish papers on stochastic processes for many years after his original papers on Brownian motion. He developed what is now called the Wiener-Klinsche theory in 1914, years before Wiener of Klinsche. Einstein published a number of papers on gravitation and relativity in 1914. The year before his famous 1915 paper on general relativity, he defined the autocorrelation functions as well and introduced a quantity called the characteristic, which is related to the intensity curve and the power spectrum. And equation is commonly called the Wiener-Klinsche theorem, and Einstein is credited with originating it. Another protagonist in this historical narrative is Lavoisier, who revolutionized nearly all previous conceptions about matter. He introduced the role of oxygen in combustion and explained the true nature of fire. He also famously decomposed water and proposed the conservation of mass in chemical reactions, among many other groundbreaking ideas, of course. He proposed the question, why should things always react in the same way? In answer, Dalton in 1803 proposed the existence of atoms. If there are atoms and these atoms react to form new substances as fixed combustions of atoms, then substances must react in specific proportions. Later on, Avogadro, who in 1811 introduced a simple yet profound idea, he suggested that the number of gas molecules in a given volume is the same for all gases, regardless of their nature, size, or mass. This was the birth of Avogadro's number, a concept that would revolutionize our understanding of matter. Celsius proposed a new interpretation of heat from a kinetic or atomic perspective, formulated thermodynamics, and introduced the concept of free mean path, the average distance that a molecule travels before colliding with another. Maxwell challenged Clausius' assumption with all molecules moved at the same speed, and Clausius argued that the temperature was proportional to the average kinetic energy, making it stochastic. Maxwell also showed the molecules move with all speeds, but the fractional number at each velocity is distributed according to a Gaussian distribution. Clausius argued that the temperature is proportional to the average kinetic energy, making it stochastic. As we dive further in the realms of scientific explanation, we delve into the extraordinary contributions of Ludwig Boltzmann, a physicist whose work led to scientific developments in statistical mechanics, thermodynamics, and the concept of atoms. Boltzmann's inquiries stemmed from the erratic movements of atoms, seemingly moving in all directions at different speeds. His questions and subsequent answers led to the formulation of one of the most famous equations in science, the Boltzmann equation. This equation describes the evolution of the probability density of position and the velocity in a gas, accounting for external forces and collisions between particles. Through his work, Boltzmann established the beginnings of stochastic processes as a field, a concept that has found applications across physics, astronomy, chemistry, and plasma physics. Boltzmann's work, of course, intertwined atomism with entropy, suggesting that thermodynamics was essentially statistical in nature. Critics argued that if a fundamental flaw could be found, the entire concept of atoms could be deemed absurd. Loschmidt presenting the reversibility argument, which suggested that if particles reverse their velocities at a certain point in a time, they would trace back to their initial positions. Poincaré and his student Zermelo proposed the recurrence argument, which suggested that for a certain system, the system would eventually return to nearly the same initial conditions over time. Boltzmann struggled to understand the opposition to his theories, despite the backing of some of the greatest scientists of all time. Wilhelm Oswald was a prominent figure in the field of chemistry, known for his contributions to electrochemistry and physical chemistry. He proposed an alternative theory called energetics, which excluded the need for atoms. Ernst Mach, another towering figure in the field of physics, was known for inspiring Einstein's work. The atomic debate was a comprehensive societal discourse, with Berthelot's works leading to governmental decrees in France against teaching atoms. Oswald eventually changed his views in 1908, but Ernst Mach remained unconvinced. Furthermore, we delve into the fascinating life and remarkable contributions of one of the great physicists of the last century, Paul Langevin. Langevin, a student of Pierre Curie, was a famous physicist who made important discoveries on the magnetic properties of materials and worked on sonar and electronics later in his career. His paper is credited with the birth of stochastic differential equations. In that paper, he aimed to derive Einstein's equation for Brownian motion in a more physically transparent way, but it also gave credit to Buoy and Shmulowski. Langevin used Newton's equation to introduce the concept of a random force, which was a first in history. The fascinating world of mathematical finance and stochastic processes has the figure of Louis Bachelard, considered one of the fathers of these fields. Although centered on the topic of stock prices, his lifelong passion was probability and stochastic processes. Bachelard's groundbreaking thesis presented ideas that have become a fundamental part of stochastic processes. His thesis committee was no less than an assembly of the greatest minds of all time. One of the Bachelard's significant contributions was his idea about the transitive property of a probability distribution. Interestingly, his solution to this was later derived independently by Einstein. 5 years after Bachelard, however, Bachelard's life was marked by hardship and struggle. His groundbreaking work was not widely recognized during his life and faced difficulties also in the University of Dijon. Despite this setback, Bachelard's impact on mathematics and finance cannot be overstated. The advent of the vacuum tube revolutionized the world and triggered the intensive study of noise in electrical engineering. electricity and magnetism became one of the most significant intellectual challenges since Newton, culminating in Maxwell's equation, a high watermark in intellectual accomplishments. The practical applications of electricity quickly expanded, with interventions like the stock ticker and light bulb dramatically altering society. The vacuum tube revolutionized technology, enabling worldwide communication and giving birth to radio. As the vacuum tube became integral to future electrical innovations, the study of noise became crucial. Pioneers like Schottky, Johnson, and Nyquist made substantial contributions to understanding noise in vacuum tube and subsequent semiconductor devices. In conclusion, the vacuum tube advent, the study of noise, and the growth of electrical engineering fundamentally shaped the 20th century technological landscape. Walter Schottky was a physicist who made fundamental contributions to various fields of physics, such as vacuum tubes and solid-state physics, and many facts carry his name. He wrote a milestone paper in 1918 where he considered both shot noise and thermal noise. Shot noise is a result of the random arrival of particles like baseball or raindrops, which create instantaneous fluctuations in the current around the average. Thermal noise is due to the random movement of loose electrons in a conductor, which can produce momentary current fluctuations. Johnson was an experimentalist who did fundamental experiments on what is now called thermal noise, and he clarified many issues related to noise. Johnson and Nyquist published back-to-back papers in 1928 on thermal noise, where Johnson reported experimental results and Nyquist gave a general and elegant derivation of the effect. Also, the field of stochastic processes or the mathematics of noise was developed independently by Batchelor, Einstein, Smirnovsky, and Langevin. There are two different approaches that have been developed in the field of stochastic processes, the Langevin approach and the Fokker-Planck one. The Langevin approach starts with Nyquist's law for the situation and puts in the stochastic force as it was like any other force, and then imposes the statistical properties of the random force. It is based on Langevin's idea. The Fokker-Planck approach, on the other hand, is based on the probability density function and involves finding the probability of a particle being at a certain location at a certain time. It is based on Fokker and Planck's work. Both approaches have advantages and disadvantages, and the choice of approach depends on the specific problem at hand. Noise had a great importance in astronomy, which is critical as it impacts almost every aspect of the field, both theoretically and experimentally. Spectral lines are also an important area of study that have contributed significantly to our understanding of the universe. Spectral lines have widths that are an indication of environmental parameters, such as temperature and pressure, and these widths are fluctuations or noise. Interesting is also the theory of pathological functions that are functions that are continuous everywhere but nowhere differentiable. These functions were initially thought to have no practical use, but were later found to be critical to understanding Brownian motion. Norbert Wiener is also a prodigious mathematician and scientist who made significant contribution to the realms of physics, engineering, and especially to the domain of modern electrical engineering. His works form the backbone of control theory, filtering, stochastic processes, and noise studies. Despite this important contribution, Wiener's work has often been misunderstood. It's essential to note that his major contributions were in defining measure for Brownian paths and developing a certain mathematical perspective on the subject. A fundamental concept in mathematics and stochastic processes he derived was Wiener process. It is a continuous time stochastic process that exhibits random, unpredictable behavior and is widely used to model various phenomena in fields such as physics, finance, biology, and engineering. Quantum mechanics is the most successful theory devised to understand the workings of the universe, from atoms to molecules to solids to transistors to lasers. It is probabilistic and produces a new kind of noise called quantum noise. Quantum mechanics deals with operators and state vectors or wave functions instead of classical functions and uses sort of probabilities in quantum statistical mechanics, incoherent probabilities and probabilities due to ignorance. Quantum mechanics is important in the understanding of the noise, especially in semiconductors and the master and laser field of quantum optics. Quantum noise is an active area of research, and many fundamental problems remain unsolved, such as the quantum Langevin equation and the quantum Fokker-Planck equation. In conclusion, the field of noise has a vibrant history filled with significant scientific, mathematical, and technological contributions. It is far more than just a study of fluctuations above the average, as it encompasses a wide range of phenomena and concepts. Noise has been developed and understood by some of the greatest minds, including Einstein, leading to remarkable conceptual innovations and practical accomplishments. Throughout its history, noise has played a crucial role in solving complex problems and advancing various disciplines. From the mathematical foundations laid by Wiener in defining Brownian motion to the quantum noise explored in quantum mechanics, and the laser noise has continually presented new challenges and opportunities for exploration. As we bring this presentation to a close, I'd like to extend my sincere thanks to all of you for your time and attention that you paid. Thank you.
Thank you, Kristi. Good work.